Alright, this video is going to focus on Chapter 11, which is going to be talking all about gases. A lot of this should be reviewed, but there's going to be a couple of new things, I suspect, for most of you. So just in general, gas properties, that they will take up all the space that's available to them. They are easily compressed, they mix with other gases thoroughly, and they are able to exert a pressure, your force per unit area, on the surroundings. Ideal gases are capable of doing all of this. The gases that you experience tend to be real gases, and we're going to talk about the difference between those towards the end of this chapter. Real gases are sometimes will attract to one another and will not necessarily fill up all their container because of that sticking together. Typically, though, our gases for a given pressure and temperature are going to be more closely resemble ideal gases. We can measure pressure of a gas using a barometer. This is how atmospheric pressure is measured. The atmospheric pressure pushes the column of mercury up the barometer. A gentleman by the name of Torricelli came up with this. And at sea level, your atmospheric pressure will be pretty close to 760 millimeters of mercury. When we have low pressure fronts come through, that pressure drops. When we're under a high pressure front, the pressure tends to be much closer to 760. Manometers are also used to measure pressure. They're specifically used to measure the pressure of a gas that's been collected in a container by looking at the difference in the mercury levels between the gas that's collected and the atmospheric pressure. When they are the same, you will see the mercury levels be equal, but it's kind of like a seesaw. If you connected A to C, we would see that A is pushing on C, so A has a higher pressure. And over here we see that C is pushing more on A, so C would have the higher pressure. But that the difference between the two pressures is going to be the height that is represented in both of those graphics. So these are our pressure conversions, that an atmosphere is equal to 760 millimeters of mercury or 760 torr. And then the metric conversion is 101.325 kilopascals, or 101,325 pascals. So we're going to do one quick conversion with pressure. We're going to see how many torr are equivalent to 57.9 kPa. So we start with what we're given, cancel out the kPas, go to torrs, and then 760 gets to go with torr, 101.325 gets to go with kPa. The kPas cancel out, multiply across and divide. We want 3 sig figs, 434 torr. And you can kind of take a look at these compared to the pressure conversions I just showed you. The 57.9 falls about halfway between 0 and 101.325 kPa. 760 torr was equal to that 101, and this is about half of that as well. If you need to pause, I would do so now. So these first few slides should be review. Boyle's law is that inverse relationship between pressure and volume. The units for pressure and volume can vary as long as they are consistent. If the pressure rises, the volume needs to decrease. We did this with marshmallows in first year chem. Sorry, I just wanted to get it all on one slide. So we have 35 mils at standard pressure. Has the pressure is risen to 2.5 atmospheres. What is the new volume? So P1V1 equals P2V2. Standard pressure and standard temperature, STP, are 0 degrees Celsius or its equivalent, and 1 atmosphere or its equivalent. So for standard pressure, we're going to use ATM units since our second pressure is in atmospheres. So standard pressure will be 1 atmosphere. The volume will be 35 mils. That's the one that's associated with it. P2 will be the 2.5 atmospheres, and V2 is what I'm solving for. So I divide both sides by 2.5 atmospheres. I should expect my volume to decrease. The atmospheres cancel out. And I get that the second volume is 14 mils. Our pressure a little bit more than doubled, and our volume dropped to a little less than half of the original amount. So that makes pretty good sense. If you need to pause, I would do so now. Charles' law is the direct relationship. This is the volume versus temperature. This kind of explains why your tire air volumes will increase or decrease depending on the temperature outside. Your volume units can be whatever you would like as long as they are consistent, but your temperatures have to be in Kelvin because we cannot have a negative volume. So if we have temperatures, one negative and one positive in Celsius, if we don't convert to Kelvin, we would get a negative volume, which is not possible. So the volume of a gas is doubled from 25 to 50. The original temperature was 25. What would the new temperature be in Celsius? Again, please remember you have to convert to Kelvin. So if we start with that gas law, V1 over T1 equals V2 over T2. We have our two volumes, 25 mils and 50 mils. We need to convert our temperatures to Kelvin, so 25 Celsius becomes 298 Kelvin. And we're going to solve for T2 in Kelvin first, and then we're going to convert it back to Celsius. So there's the 25 mils and the 298 Kelvin. There's the 50 mils and what we're solving for. Cross multiply and solve for your unknown. Cancel out your milliliters by dividing both sides by 25. And we get that the temperature that doubled is the Celsius, excuse me, not the Celsius, but the Kelvin temperature, which is 596. We would expect it to double since the volume doubled. But to get it back to Celsius, we need to take 273 away, and that gets me 323 degrees Celsius. So if you just try to double the Celsius temperature on a problem like this, you would not be able to get the correct answer since the relationship exists for only Kelvin temperatures. If you need to pause, I would do so now. So a couple other laws that we haven't focused on as much before, but that are pretty similar. Avogadro's law, which relates volume to amount. And basically, the greater the volume, the more of the gas you have. So it's a direct relationship. And again, as long as the units are consistent, then we're good to go. So quantity would need to be in moles. You can't use grams because we need to be able to compare the quantities to one another. So 0.1 moles of oxygen gas occupies a volume of 15 mils at 0 degrees Celsius. What would the volume be of 0.3 moles of oxygen gas if it was at the same temperature and pressure? Since the temperature and pressure aren't changing, they won't be involved in this gas law, so this truly will just be about the volume and the quantity. We have that 15 mils is the volume for 0.1 moles, and we're trying to find what the volume would be for 0.3 moles. Our mole quantity tripled, so we would expect that since this is a direct relationship, our volume should also triple. Cross multiply, solve for your unknown. You should start seeing a pattern here if you haven't already. The moles cancel out on the left, the 0.1 moles cancels out on the right, and we do indeed get a tripling of our volume from 15 to 45 mils. If you need to pause, I would do so now. Just so this one doesn't get left out, Gay-Lussac came up with a relationship between pressure and temperature, that it's a direct relationship if everything else is being held constant. And again, because temperature is involved, it would have to be in Kelvin. I didn't give you any examples with that one, so we're going to move on. Combined gas law relates pressure, volume, and temperature. So we don't just have two things changing, we have three. The quantity is staying constant. Same rules apply as they did in the individual gas laws, but your temperatures have to be in Kelvin. So we have 45 mils of an ideal gas that's at a temperature of 15 Celsius and a pressure of 740 millimeters of mercury. The volume got doubled. The temperature was reduced by 1/3. What is the new pressure? So P1V1 over T1 equals P2V2 over T2. We have all of the initial conditions. We just have to convert that 15 Celsius into Kelvin. So there's the 740 millimeters of mercury, the 45 mils, and the 288 Kelvin. And now we're going to find out what the new pressure is. So P2 is our unknown. We're told the volume doubled, so 45 doubled would go to 90. And when we're finding out the temperature, we're taking 1/3 of the 15 degrees Celsius, which would take away 5, which leaves me with 10 Celsius. And then I would add 273 to that to get 283 Kelvin. Cross multiplying, I get the 740 millimeters, the 45 mil, and the 283 Kelvin together. And then I have P2, 90 mils and 288 Kelvin. I can cancel out the 90 mils and 288 Kelvin on both sides. So that takes care of the milliliter units as well as the Kelvin units. And this is just one way you could solve this one. You could do the math first and then divide whatever you like. And you should get a pressure in millimeters of mercury. We want 2 sig figs because of the volume measurements. And that'll be 360. If you need a pause, I would do so now. Alright, we're going to stop here for this video. I'll do ideal gas law and I believe stoichiometry in the next one.